welcome everybody. So it's always interesting to find people who spend a bulk part of their life doing technical stuff. So it's my pleasure to introduce Hans Reiser. He's the creator of Reiser file system. And this talk is going to be covering both the ideas, the background, the algorithms, and the life of Reiser 4. Is correct?
So I'm going to tell you a little bit about our corporation before I get going. We have a group of programmers, most of whom work in Moscow, one in St. Petersburg, one in San Francisco. I'm in Oakland. Back in 1993, I went to Russia and hired a team of programmers, and that allowed me to avoid having to engage in venture capital. And so in this talk, I'm going to discuss how unifying namespaces improves closure within the OS. I'm not really going to discuss the semantics that I want to use because that would take me way past my time limit. I am, however, going to discuss performance and the ways in which we accomplish a high-performance storage layer, and these various other items that are on the slide. I would like it if you would ask questions during the course of the talk, because the difference between my website and my talk is that I answer the questions. And so the natural question is, well, so what is it that the Reiser 4 is trying to accomplish? Well, hierarchy doesn't scale well for human beings, and hierarchical namespaces scale extremely poorly. Relational databases also don't scale well. There's a reason why relational databases are not used for searching the web. And the reason that they don't scale well is because they add structure to information, structure that is not inherent in the information. But at the same time that they add structure, the problem with boolean algebra and search engines that resemble boolean algebra and what they do is that they don't allow you to represent the structure that's inherent in the information. And so what you would ideally like in a general purpose file system namespace is something that matches rather than molds the structure that's inherent in the information. And if you can't match rather than mold the structure that's inherent in the information, then you're better off using something that resembles boolean algebra. And I think you folks all know why that works better. Because, well, let me just state it formally. If you have a choice between ignoring known structure, so if you have a choice between not allowing the user to use structure that they know about and that is present in the information versus requiring that they use structure that's in and thereby requiring that they learn the structure that you require in order for them to be able to use your namespace, you're better off ignoring the structure than requiring it. But ideally what you would like is to match the structure inherent in the information when you insert it into your namespace. And you would also like to allow the user to specify what random fraction of that information he knows and use it in his queries. And structure, you can think of structure as just one more random piece of information that the user happens to know when they're looking for something. The file system is the most central namespace of the OS. Now, this was probably more true 20 years ago, but it's still substantially true. even with the advent of search engines and the web. And I would like to suggest to you that namespaces in general are like roads and waterways. And in 1776, I think it was, Adam Smith wrote a book called The Wealth of Nations. And in this book, he suggested that civilization tends to develop around roads and waterways. And the reason for that is connectivity. Where you have roads and waterways, you increase the amount of other people that you can interact with if you're on that road or waterway. And he found that there was a very tight correlation between where civilizations tended to develop and where there were roads and waterways. And I would like to suggest that in general, in a great many large systems, the power of the large system or the utility of the large system is proportional not to the number of components in the large system, but to the connectivity of those components. And in particular, I'd like to suggest that for an operating system, its expressive power is determined not by the number of objects that you pay for the development of within the operating system, but instead, excuse me, it's proportional to the number of connections between the components. And these components are, in general, connected by the namespaces of the operating system. It's the namespaces that conduct the interactions between these objects and that serve as a unifying bus along which all of these different components can communicate with each other. And if you have a unified namespace instead of a fragmented namespace, then you have more connections with a unified namespace than with a fragmented namespace. A trivial example of that is, well, if you have a choice between two namespaces, each holding half of the components, versus one namespace holding all of the components, the one namespace is going to have more total connections because it will be proportional to n squared instead of n over 2 squared. And you have a great variety of different namespaces within the operating system. You have the web, you have the file system, you have databases, you have environmental variables, you have a whole bunch of different namespaces within the operating system. And to unify the namespaces within the operating system is a bit of a quest for a holy grail. And by that I mean that King Arthur sent his knights out to find the Holy Grail, and if only they could become good enough, the Holy Grail would appear to them. None of them ever became good enough that the Holy Grail appeared to them, and yet the quest for the Holy Grail made them all that they became. And so, even though we will never succeed in unifying all the namespaces within the operating system, the closer we can, if we can just get ourselves closer to it, we're in a better place than if we don't get any closer to it. Yes?
Could you clarify a little what you mean by the fragmented nature of the namespaces? What different namespaces are you trying to unify?
Well, so for instance, you typically have, say, an Oracle database, which has a whole bunch of pieces of information within it and components within it. And these components aren't part of the same namespace as the file system namespace. And so you have a whole bunch of utilities that are designed to use the file system namespace, but aren't able to casually interact with the Oracle namespace or or any of the various other namespaces. Another example is if you look in /etc, you have a great variety of different file formats. for all kinds of different things that are recorded in various flat files within /etc. And each of these different files has its own syntax, its own way of being parsed, its own way of recognizing that this is an object. And those are all fragmented namespaces. And it's convenient when you can just say, oh, another example of a fragmented namespace is the metadata for a file. So the owner of a file you can get using the stat command, the stat system call. And this is a different namespace from the namespace for accessing file bodies. And if those namespaces were unified, then you could do something like cat file name A greater than file name, cat file name A slash slash owner space greater than file name B slash slash owner, and thereby set the owner of B to be equal to the owner of A. And you can do a whole bunch of little tricks and a whole bunch of little convenient things if you have unified namespaces that allow you to casually connect the output of one object or the data that is one object to another object within the operating system. Okay? Yes?
Successful kind of big namespace, they work also on the spread across multiple machines, which would mean that operations of an object within the namespace gets found on machines in the network, which would imply that file system would extend to protocol.
Okay, so the question was, I'm going to repeat it because I think you were inaudible. The question was, should this namespace span machines, span networks? And the answer is yes, but it's a holy grail, and I'm not going to get there this year. Okay? So, if you would like to read about the semantics for the file system that are what we are headed towards, and read about a set of semantics for semi-structured data querying that attempts to match rather than mold structure, that's on our website. And solely because of lack of time, I'm just not going to be able to cover that in this talk. So the first thing we decided to do when we wanted to do this integrated namespace is to deal with the problem of small files. And conventional file systems 4K align all files. And what that means is that if you want to store a phone number sized object, it's inefficient and ineffective to store that as a separate file within a traditional file system. And so we started with this problem first because it was the hardest problem. It was technically the hardest problem to solve. And the reason it was the hardest is that addressing it required a complete redesign from scratch of the file system. And in particular, we had to design a file system that's based upon balanced tree algorithms. And a balanced tree, to put it very simplistically, a balanced tree takes a whole bunch of small little items and squishes them together. Maybe I should do that as, and squishes them together. And stores a whole bunch of small objects in one 4K node. There was a problem with doing that. And the problem with doing that was that it was generally accepted that balanced trees were performance ineffective for traditional file system usage patterns. And that it had been tried and it was considered a failed experiment. And I was told this by more than one person. And the problem, and so what it turned out was that there were problems with the algorithms that were used in balanced trees in traditional databases that were the reason why it was performance ineffective to use them for traditional file system usage patterns. And so we had to fix those problems in order to make it work, and that's why it took 10 years, quite simply. So let's talk about the implementation. So the general idea in the file system is that you have objects, and these objects exist in the, you have objects, and these objects, we chop them up into little items. And the items we squish together into our nodes. And so nodes are 4K in size, and there's nothing magic about that. It just happens to be easy to code that way in Linux. And an item is a portion of an object that is small enough to fit into one of those nodes. And for every item there is a key, and items are fully ordered in the tree by their key. So this means that we have added an abstraction layer to optimizing disk layout. So if we want to completely change how things are laid out on disk, and completely change what kinds of items tend to be aggregated with what other kinds of items, what we do is we just change our key assignment algorithm. And this means that if we want to try something completely new about how to stick something with something else, we can, in a couple of hours of code, accomplish a change that in another file system would possibly take 6 months to code. And it might take more than 6 months to code because in another file system would probably require a change in disk format. And disk formats are the grand bugaboo of file systems. File systems have great difficulty changing disk formats once they get out there. And it's extremely painful and expensive for any OS distributor to change a disk format for a file system. And that tends to mean that when you write a file system, you have to get your disk format right the first time. And nobody gets it right the first time, and so everybody suffers. And by adding this abstraction layer, and by using our plugins, which I'll get into later, we completely avoid that. And file system performance is highly empirical. You can measure the performance. You can measure whether you got it right. And the thing that's true of everything that's highly empirical is that you're going to get it wrong a lot of the time. Because nature is just so much more complex than our puny little brains. And so how well your file system performs is very much determined by how easy it is to make little changes to it. And the more little experiments you make, the higher your performance is going to be. And by doing things like this key assignment abstraction layer, we make a lot of things that for other file systems are a lot of work to code, for us into a small amount of work to code. And that gives us performance advantages. And later I'll talk about some performance advantages that were required primarily because for us it was a small amount of code to experiment. Well, I guess that's actually the next slide. In the Reiser4 file system compared to the Reiser3 file system, in Reiser4 the keys for file bodies have the same order as keys for the first directory entry they are created with. And this turns out to have a 2x performance, gives us a 2x performance increase for operations that occur in read-your order. And it turns out that there's quite a lot of applications that access a bunch of files in read-your order when they go through a directory operating on them. And it's also useful in that if you get a performance advantage from going through things in read-your order as an application, you can frequently choose to go through things in read-your order and get a performance advantage from it. Now, the disadvantage to what we did is that it made our keys larger. So in order to make the keys for the file bodies be in the same order as keys for the first directory entry, we had to put some information, some extra information into the key. Changing the code to try this new key assignment order was something that the programmer asked to do, it just didn't want to do. And he told me it would take him 6 weeks, and it actually took him 3 days. And I think the next time we did it, it would probably take him about 3 hours, because in the course of making the change, he cleaned some things up to make it easier. And this got us a major performance advantage by performing this experiment. And this experiment might or might not have happened at all if it had taken us 6 months to perform the experiment, or even 3 months to perform the experiment. Probably wouldn't have taken us 6 months, but it might have taken us 3 months in version 3 to do it. Yes?
What key assignment did you use in earlier versions of Reiserfs? So what changed?
Well, in the earlier versions, the file bodies are ordered first by the parent directory ID, and then by the object ID of the file. And the object ID tended to get created in time order. And some of the time that was good, and some of the time that was bad. And unfortunately, because of the length of the talk, usually I give you a complete discussion of how you resolve a key in the course of finding something within the tree, and I think that's going to be one of the things that I drop. So let's talk about B trees. In the traditional B trees, the data was stored in the internal nodes. So in B plus trees, the major innovation was that you shoved all the data down, farther down into the leaf level of the tree. And the effect of doing this is that you increase fan-out. And fan-out matters a lot. Fan-out determines two things. One of them is that it determines the cacheability of internal nodes. So if you have, if your internal nodes are less than 10% of the total amount of nodes, it makes a big difference in your ability to cache all of the internal nodes. Another advantage that it gives you is that you tend to have seeks cropping up when you cross boundaries between internal nodes. And in version 3, seeks tended to get added when balancing changed who the parent was. And two things improved that in version 4. One of them was allocation on flush, which I'll get into later, and the other was increasing fanout. Now, with respect to caching, I'd like to say that caching is dependent on temperature invariance. Now, you can think of, I should say, by temperature what I mean is the tendency to access a certain object. So some objects tend to get accessed more frequently than other objects. And for caching to work, it's dependent upon there being a temperature invariance. There being a temperature variance. If there is no variance in temperature between objects, if there isn't at least a temporary, short-term, time-based variance in the frequency of accessing objects, then caching cannot work. Segregation can increase temperature variance. And by that I mean that if you have two sets of objects that have different average temperatures, and if they are stored in some larger containers that are the units of caching, then segregating them can increase the temperature variance. So if you take all of the pointers and put them in one set of nodes, and then you put the data in another set of nodes, and if by doing this you increase, and if the pointers tend to have a different average temperature from the data, then by doing this you have increased the temperature variance. And so if you think about it, for all of the pointers, when you go through them to find the data in the tree, in order to get to the data, you have to go through one of the pointers. So, I'm sorry, in order to get to one of the leaf nodes, you have to go through one of the pointers. So each of those pointers is, on average, worth as much as an entire leaf node. And so that naturally tends to suggest that pointers, on average, have a higher temperature than data does. Version 3 of Reiserfs, and most databases do this also, since they also use blobs, they unbalance the tree. So in the original papers describing blobs, their idea was they would, for objects that were too large to fit into a 4K node, they would insert into the tree a bunch of pointers to these unformatted nodes, and they defined these unformatted nodes as not being part of the tree. Well, this may have fooled the computer scientists, but it didn't fool the computers. Just because you've defined them to not be part of the tree doesn't mean that it performs just like an unbalanced tree. And so for all of the reasons that balanced trees are superior to unbalanced trees, blobs are a bad idea as they are traditionally implemented. You have reduced fanout when you have a less balanced tree. Having an unbalanced tree reduces fanout. Mixing pointers with data gives you a unbalanced tree and reduces your fanout. In version 4, what we did was we took those blobs and we stuck the pointers to them up into what we call the twig level of the tree. So we have leaves, and above that we have twigs, and above that we have branches. And the other thing we did was we, at the same time, we also chose to use extents. And the basic concept behind an extent is you define the starting block and you define a length. And these two counters give you a whole extent. And if you do a good job in your allocation, you can define a 4 GB file using one extent. And that's very efficient to do it that way. Yes?
If you're using contiguous extents, don't you end up with problems with internal fragmentation?
He asked, if you're using contiguous extents, don't you end up with a problem with fragmentation? Did I repeat your question correctly?
Yeah.
And the answer is yes, and the answer is we use heuristics, and we can observe that they have a tendency to work. And in the worst case, extents make things worse. So in the worst case, you cannot find a the worst case, you cannot find an extent that's longer than one block. And so in the worst case, when you allocate a file, you end up allocating it in one block extents. And because the extent has to have both the count and the block number, it's a bigger pointer. And so in this worst case scenario I just defined, you have worse fanout. And one of the differences between worst case analysis and the real world is, well, you know, there's just sort of an art to knowing when you have to worry about the worst case and when in practice things are just going to work. So in practice, we tend to get good allocation. If in practice we didn't get good allocation, this would be a bad design. But in practice we do get good allocation. And there are a number of things that contribute to our getting good allocation in practice. And one of these things is that we do allocation at flush time, and I'll get to that a little bit later. And the other is that we're working on a repacker, and I hope that we have one in not too long. And the repacker, it's my belief that for our worst case scenarios, it's actually more efficient to let the repacker come in and clean things up later than to try to optimize them on the fly for the worst case scenarios. And I'm going to have to skip a little bit forward. I take that question in the back.
So I can see that this scheme will improve performance for some workloads, but are there some specific workloads where it will make things worse, like lots of frequent updates?
There are workloads for which we do need the repacker. And I believe that when you have frequent updates, you're better off having a repacker reoptimize things later. There probably will turn out to be workloads for which this is not the right approach, but I believe that this gets 99% of the user base. And I was once taught by David Hitz, the founder of Network Appliance. He said something that I thought was very valid, which is that when you're designing a product, you should go after the 80% of the market, and you need to be careful about the remaining 20%, because the remaining 20% can be the hard part, and you can end up throwing so much resource at the 20% that it distracts from solving the needs of the 80%. I'm sort of paraphrasing what he said. My apologies to David. So, traditional trees, by the way, is it going to work for the video conference thing if I draw on the board? It will, yes? If I pull this up? Okay. So, traditional balanced tree algorithms used fixed criterion for determining when to balance. And the most common criterion used So the most common criterion is if you delete something from this node. So if you delete something from this node, then you would look at this node, the left neighbor, you would look at the right neighbor, and if these three nodes can be squeezed into 2 or fewer nodes, then you perform a balancing. And you squeeze them together and replace the 3 nodes with 2 or fewer nodes. Now, what you can also do if you want tighter packing, instead of looking at the left neighbor and the right neighbor, you can look at 2 neighbors to the left and 2 neighbors to the right. And if these 5 nodes can be squeezed into 4 or fewer nodes, then you squeeze them all together and perform that analysis with every modification to the tree. And you can do it for 3 nodes to the left and 3 nodes to the right. So what is the reason why we don't go all the way to the left and all the way to the right? Well, the answer to that is how far you go to the left and how far you go to the right determines what your overhead is per modification to the tree. And so you have a memory bandwidth overhead, and you also have an overhead that's due to any of these nodes that aren't in memory at the time that you need to access them. And so what we decided to do was to be lazy about it. And we decided to, instead of modifying the tree with every modification to the tree, modify the tree in response to memory pressure. And instead of making how far to the right and how far to the left we go dependent on some fixed criterion, some fixed number, we would instead gather together an entire slum. Now a slum is a set of contiguous in tree order dirty nodes. So in this thing that I have drawn, these 4 nodes are one slum, because these little X's mean dirty. And so if VM indicates that this node is dirty and has been in memory for too long, then what we do is we come down the tree. Well, we start from here in the tree. We go all the way to the left and keep going until we get to the first non-dirty node, and then we stop here, and this is the left border of the tree. And then from here, we go in this direction in the tree. And as we go, we squeeze things all the way to the left. And if there are 100,000 nodes, we will attempt to squeeze those 100,000 nodes into 99,999 nodes. And at some point we decided that rather than try to estimate whether or not we could squeeze those nodes into fewer nodes, we would just do it. We would just shove everything as far to the left as we could put it. And that turns out to be kind of reasonable to do in terms of performance and its effect, and it makes the code a whole lot simpler. Because when you don't have to estimate, when you can just shove things to the left, well, it's a good way of calculating is to just try it and see if it works. And when we perform this squeezing, we have eliminated the overhead versus tightness of packing trade-off. And at the same time that we do the squeezing, we also have some other flush plugins that we process. So we also have encryption and compression plugins that get processed at flush time. And we also have block allocation plugins that occur at flush time. And so we have all these things that we do at flush time, and this gets us a much better result. One of the problems with compressed file systems is that they don't work so well for when you have a file set, I should say a working set that fits into RAM, and now to the computational cost, they add having to compress with every write, even though all this stuff fits into RAM and doesn't really need to be compressed. And by deferring compression until the time that we flush things out to disk, we greatly reduce the overhead cost of a compressed file system. Same thing goes for encryption. We don't really need to encrypt things when they're in memory because memory is insecure anyway. And with encryption, what we're really trying to do is ensure that when your laptop is off and somebody comes along and steals it, they can't do anything with it. We're not trying to protect you from being rootkitted. And so the disadvantage of this approach is what happens when your slum size is 1. And I would suggest we sort of made the decision, and I would suggest to you that it's valid, is that if your slum size is 1, you're better off letting the repacker do it. And you're better off letting a repacker come along, and once a week it'll go, or once a day, however you choose to make it, it'll go through your file system from beginning to end and suck things in 4 megabyte chunks and write things out in 4 megabyte chunks. And instead of trying to repack one little 4K node at a time, it'll suck in a whole bunch of poorly balanced 4K nodes that were modified during the course of the week. And I believe that's just more optimal. Our file system is designed to reduce your coding costs when using it. So we have file plugins. File plugins will allow you to create a new file plugin that will perform any arbitrary operation you want it to perform in response to a read or a write or any of the other standard VFS operations. We have directory plugins, hash plugins, key assignment plugins, node plugins, item plugins, space allocation plugins, disk format plugins, superblock plugins. The disk format plugins allow us to come out with completely new versions of Reiser 4 and not have the users have to notice it, much less reformat their disk. Yes?
Just give a few examples of practical things you use plugins for.
I was asked to give a few practical examples. Well, the compression plugin is a good one. The encryption plugin is a good one. Copy on write plugins. There's users who want to write that. There's somebody, if you want to write a clustering file system, you're going to want to have a few plugins for your cluster file system. If you wanted to implement a search engine with this as a storage layer, you could write a set of plugins to do that. And so you could create a set of objects that would be used by the search engine and have our balanced tree algorithms efficiently squish them together, store them on disk, suck them back in. And because of our item plugins, I should explain that in version 3, all the different kinds of items we have, our balancing code special cases them. And I started to realize in looking at the code that the complexity of the balancing code was going to be proportional to n squared, where n was the number of different kinds of items. And so in version 4, we have these item plugins, and the balancing code doesn't understand the internal structure of the items that it balances at all. What it does is it invokes an item plugin, and it has a set of defined methods that each item plugin must be able to support. And if you write an item plugin that supports those methods, the balancing code will be able to efficiently manage the space for those items without understanding them at all, so long as the item plugin understands their internals. Yes, sir?
Do you do any optimizations with keeping adjacent nodes and adjacent blocks on disk or anything like that? Do you do any pre-allocation of trees?
We do a lot of those optimizations. That's what determines our performance. But I would, actually I should say most of the optimization actually gets done in the key assignment area. And the optimization that we do is simple. We try to ensure that tree order correlates with disk order. So when we and when I say tree order, I mean parent first pre-order. Oops. So I've now numbered these nodes in parent first pre-order. And if we modify this node, actually let's say we modify this slump, okay? Then we look at the left neighbor of this slum, which is number 3 here, and we see what its block number is on disk. And starting from there, we search for a free block. And we then attempt to assign block numbers in this order of 4, 5, 6, 7, 8, 9. We try to put parents before their children. And so by doing that, we're attempting to optimize for tree order access, which turns out to be a good thing to optimize for. And that is the simplistic version of what we do. And there are other things that we do to handle the case where the bitmaps start to get crowded. And I can also talk about when we relocate things for small slums. say this is a large slum, then the cost of introducing a large seek is small. So if you put a large seek here and it allows you to put everything into a nice, neat order, that's perhaps worthwhile to do. Unfortunately, there's only so much time in this talk, so I have to get really glossy here. But the main point that I'm trying to make here is that working on a storage layer like this is very cost effective. It is a lot less work to do something when you have all these different layers of abstraction and you can just write a new plugin to do what you want. And you don't have to rewrite everything in order to make your one small change. And to some extent, this reflects the difference between a first generation product and a second generation product. So our first generation product, we had an idea, we just tried to get it out the door. Now, we don't want to just get something out the door, we want to have something that we'll be able to enjoy working on for a long time. And I think I'm going to skim over the miscellaneous locking. Can somebody tell me how much time I have left? 10 minutes, okay. So, in our locking, going towards the right and going up is considered high priority, and going down and going to the left is considered low priority. And what this means is that all of our balancing operations, which go to the right and go up, are high priority, and all of our searching through the tree operations are low priority. And the reason for doing that is that for our code, having to undo a balancing operation would be very expensive. But having to undo a search operation is very cheap. And whenever a high priority thing bounces into a low priority thing, when the low priority yields to the high priority. And I would give a much more rigorous description of this if I wasn't low on time. We only have time for the very simplistic explanation of a wandering log, so I'm going to give that. And that idea is that instead of writing everything twice in order to ensure that it's committed atomically, first writing it once to the journal, and then writing it to where it's supposed to be on the disk, we first write it to the journal, and then we change our definition of where the journal is. And when we define where we're going to have our journal, we happen to choose a location that's where we want things to end up being. And I could give you a much more sophisticated explanation if I wasn't sure on time. And we also have interest in making things transactional. And I'm going to skip over that. And I'm going to skip over the repacker. 80% of files don't move for long periods of time, and if you repack once a week, 80% of your files are going to be perfectly laid out for reads. And these benchmarks are old, but is it possible to connect to the internet here? It must be, yeah? Can Can somebody help me with it? No? Oh, this laptop is too old for wireless. Okay. It's okay. I'm gonna manage it. So in this file set, 80% of the files are 8K in size or smaller. 80% of the remaining files are 80K in size or smaller. 80% of the remaining files are 800K or smaller. And this sort of strange distribution function turns out to be fairly close to what real file systems have. And in most file systems, most of the files are small and most of the bytes are in large files. That would be different if the files were indexed and each of the keywords was considered to be an object. But that's the traditional statistic for traditional file system usage patterns. And so in this benchmark, we first create a bunch of files, then we copy them, then we read them, then we perform stats on them, then we delete them. And we generally get good performance. Now these benchmarks are a little bit obsolete because we just got our compression plugin working. And I don't have the statistics compared to our competitors, but in general, our code compared to our code with compression turned on, the creates take 76% of the time that they used to take, and copies are like 56%, and reads are like 55%, and deletes were reduced, but I don't remember by how much time. And for a file system, for a computer that has a decent CPU and a disk drive, the CPU can compress faster than the disk drive can write. And this is a change in technology that's happened in the last 10 or 20 years, that CPUs have been getting faster than disk drives have been getting faster in their transfer. So CPU compression time has improved compared to disk transfer time. And so now a compressed file system is higher performance than an uncompressed file system. And you can improve your performance by using compression. And I'm going to stop with giving the talk and get to the questions, which are the important part.
You tried your benchmark using what should be called as a real-world application, like in compiling a large software package, see which one is better compared to the institute. Okay, now we'll talk about somewhere we configure things that install.
Yeah, I tend to let our users do that, and they post. I'm sorry, I should say what the question is. Have we done real-world benchmarks like compiles? And the answer is yes, and our users have done them. And I am pleased to say that the kinds of performance that I get in this benchmark, the users tend to report getting similar performance improvements. And to get a really thorough answer to your question, you should ask my mailing list, Reiserfs-list@namesys.com. And you know, if you want benchmarks that you can rely on, you don't ask the author, you ask his mailing list. Yeah. I should say that in version 3, one of my great disappointments was that when you turn on tails, so that you squish those files together, we got a performance drop when the file size was randomly within the 1 to 10K size range. And I have since understood that actually with FFS, when they introduced fragments, one of the things that they didn't put into their paper was that there was a performance drop from combining those tails together. So whenever you take multiple pieces of different files and squish them together, and you have to be careful that you don't introduce seeks. And with version 4, we don't introduce seeks, and with version 3, we did. And so now with version 4, if you efficiently store the small files, you get a performance increase, period. And with version 3, you had to pay a performance cost because we were introducing seeks. Questions? No questions? Yes?
Question with metadata, there has been some reports that at some point Reiserfs will support metadata like Unix. So what are the plans?
So I gather you're asking, will Reiser4 support accessing the name of the owner of a file within the file system namespace? Is that what you're getting at?
No, the arbitrary metadata, like in Unix, you can interpret your file system as arbitrary objects with arbitrary attributes, and then you can query the object collection by the attributes and do things like that. So it's not exactly relational, but has more relational similarities than typical file system.
Yeah, we want to do that stuff. I should repeat your question. I think your question is, when FS allows you to query the metadata, will Reiser4 allow you to query the metadata? Or just act, what?
Yes.
That's correct. Okay. The answer is yes. We want to be able to do that. The code isn't currently there. It should be done. It's part of our direction. We'll get there. And it will be sadly political, the road to get there. And we will overcome those political problems.